In this problem, we have this 30 kilogram disc that is supported at its center. So we apply a moment of 5 Newton meters and a force of 10 newtons to this disc, and we're interested in figuring out, if it starts from rest, how many revolutions does it take in order to get to 20 radians per second. So how many times does it spin around before it gets an angular velocity of 20 radians per second? So let's start with a free body diagram, like we always do. And we're going to identify the forces as this 5 Newton meter moment, this 10 Newton force that we're pulling on, and we're going to identify these reaction forces in this pin. We're going to say that there is a reaction force in the positive y direction and a reaction force in the positive x direction. And finally, we have to account for the weight. The weight is going to be acting straight down. The disc is uniform, so it's acting straight through the center. And its weight is going to be its mass times gravity, so it's going to be 30 times 9.81. And this is going to be equal to its mass times acceleration. But it's a fixed disk, right? This center is not moving. It's fixed. It's just rotating about its center. But it's rotating, so it's going to have this component. It's going to have its moment of inertia about its center point times its angular acceleration. We don't know which way this is going. It's probably not going this way, but we're going to assume it's positive. If it's negative, negative sign will take care of everything. But now we can look at our 3 equations we use. The sum of the forces in the x direction is equal to a mass times an acceleration in the x direction. The sum of the forces in the y direction is equal to a mass times an acceleration in the y direction. And an acceleration, and the sum of the moments about some point is equal to the moment of inertia about that point times the angular acceleration. So if we look at the sum of the forces in the y direction is equal to a mass times an acceleration in the y direction, we don't have any acceleration in the y direction. So this part of the equation, this side of the equation, goes to 0. So now we just have to sum our forces in the y direction. It's going to be positive is up. This weight is a minus, so it's minus 30 times 9.81 plus this reaction force, Fy, minus this 10 newtons. And this is equal to 0 because there's no acceleration. And if we solve out for this reaction force, this Fy, we're going to get this reaction force Fy is equal to 304 newtons. Now, we don't need to sum the forces in the x direction. It's just sort of a trivial case right here. There's no forces in the x direction besides the reaction forces, no acceleration. So there, this force f of x, there is nothing. It's equal to 0. So I'm going to skip over that. But I am going to sum my moments about point G. And this point G right here is the center of mass. And it's, in this case, also it's point O. So the point that it's rotating around. So if we sum our moments about the center of mass, because now we have a rotation, it's not equal to 0, it's equal to the moment of inertia about the center of mass times the angular acceleration. So this way is going to be positive, and if we sum everything up, we're going to get a minus 5 Newton meters. The weight goes through the center. This reaction force in the Y goes through the center, so they don't create a moment on the system. But this 10 newtons doesn't go through the center, and it has a perpendicular distance of the radius of this disk, which is 0.2 meters. It wants to rotate clockwise, so if we rotate it in this direction, it's going to be a minus 10 times 0.2, and it's equal to, we're assuming this is going positive, so moment of inertia times alpha. And let's figure out what our moment of inertia is. It's a uniform disk with a mass of 30 kilograms. So if we go and look at the table in the back of the book, we're going to get that our moment of inertia about this midpoint is going to be equal to 1/2 mr squared. This is just a formula you'll find in the back of the book. So this is going to be equal to 1/2 30 times 0.2 squared, and this is going to be equal to 0.6 kilogram meter squared. So this is a 0.6. So this right here is going to be equal to 0.6. So we can fill that in. Okay, and now we have this equation, and we can solve for alpha. And we get alpha is equal to negative 11.67 radians per second squared. What does this tell us? This tells us this assumption was wrong. It's actually rotating in the opposite direction. So alpha is equal to 11.67 radians per second squared, going clockwise. And we're going to use this piece of information right here to figure out how many revolutions we need to get to 20 radians per second. Now, this is sort of kinematics. We know that we start from rest, so our angular velocity when we start is equal to 0 radians per second. We're interested in getting to 20 radians per second, so the angular velocity we want to get to is 20 radians per second. Our angular acceleration is equal to minus 11.67 radians per second squared. And we're going to say our initial angle, our initial angular displacement, we're just going to start at 0. Oops. We're just going to start at 0. Okay, so using this, we can use those sort of kinematic equations for rotation about a fixed axis, and we can do this one of two ways. We can use the equation that has a square in it, if you remember that. If you don't, we can solve it like this. We can say our final angular velocity is equal to our initial angular velocity plus our angular acceleration times time. If we plug in 20 here, it's equal to minus 11.67 times t. We can get a time which is equal to 1.71 seconds. Using this time that we get, we can use another kinematic equation. We can use that our displacement is equal to our initial displacement. So this is our final displacement, is what we're looking for, plus our initial angular velocity times time, plus 1/2 times our angular acceleration times time squared. And if you know what we're doing, this is going to simplify. It's going to be 0 because we're going to call this 0. It starts from rest, so this is 0. And we get a final angular displacement is equal to 1/2 times minus 11.67 times this 1.71 squared, and we get a final theta, which is equal to minus 17.05 radians. Now, what does this mean? This means, well, everything in this problem was dimensioned with this being a positive. So our radians are actually it's actually going the other way. It's going 17.05 radians in this clockwise direction. So if you, I know I said find how many revs to get this, but I found it in radians. You can convert radians to revolutions by dividing it by 2 pi. So we'll have this is equal to 2.73 revs. This really is not the important part of the problem. The important part, sort of, how do we get to this part? But this negative sign on it just means it's going in the opposite direction, since we used counterclockwise as our positive notation for this problem.